Here we go into our penultimate lecture, the second to last lecture of the class. We're going to formally define hidden Markov models, talk about all the little pieces, a fairly elaborate definition by our standards, talk about all the pieces in that, and start to kind of make sense of what kind of a useful thing might we be able to calculate among the many different things you could calculate. And what might be the kind of cost or the things you might need to do that. All right, let's start. So we're going to pick up where we were last time, which was talking about hidden Markov models, which we had just sort of barely introduced. So I want to just remind you of the key ingredients. So the first item was the observed process. So there's two stochastic processes that we want to talk about. The first one is the observed process. And we'll write this guy as follows: x sub t such that t is equal to, and we're using a convention where we start at 1, which is kind of different from what we've done in previous sections of the class. And the aspects of this thing that are important to remind yourself of are that it's a discrete time process. And that the values that the random variable can take on could be either discrete or continuous. So it could be a discrete, so depending on the problem of interest, or a continuous, which is new for us, sort of, continuous state space. And the other thing is it's got other names, the observed process. So we sometimes call it the state-dependent process. All right. The other key ingredient to the hidden Markov models is the second stochastic process, which is a Markov chain, and that one we call sometimes. There's different names that you can call these by, but we're going to call this the unobserved process. Oops. And the label we'll use for it is capital S with a subscript of t. And so the same rules for t, 1, 2, and 3, and so on. And this guy's properties are similar. So it's discrete time. I think that's probably somewhat obvious, maybe. But the state space is discrete. And it's going to be a Markov chain, or you could call it a process, but then you might get mixed up with the idea of continuous time. So you might want to call it you can call it a discrete time Markov process if you want. Or you could just call it Markovian. Let's do that. Or just call it Markov. And it also goes by another name pretty frequently. We call it the parameter process sometimes. And I think we said before we called these things the states, and these guys up here are the state-dependent process. So we walked through some examples of pairs of processes like this that we might want to consider. And I thought I would just make like a little table of a collection of other examples. So just to kind of get your mind thinking about things that you could study with hidden Markov models. So we'll just say these are examples. And we're just going to make a little table. On one side there's observed, and the other side there's the hidden process. So the observed is x sub t, so we'll call this observed. And the hidden is s sub t, so we'll call this hidden. And we're just going to make just a collection of ideas, really. We're not going to work these out in detail, but just to kind of see what kind of things might you pair together. All right, so one we have in the notes, but we didn't really discuss last time, was like an animal, and for that, the observed process was whether or not the animal was feeding. So we'll say feeding or not. So maybe you have some cameras or something like that, or you just sit around watching the animals and you record whether or not the animals are feeding. And then the hidden or unobserved thing is whether or not the animals are hungry. Okay, so that's one example that we kind of described in the notes, but not in the lecture. The other one, it's also in the notes, but similar to one that we had in the lecture, was like a movement rate or a speed. And so that would in principle be kind of a continuous process, a state space, whereas the feeding or not was not, it's just binary. And the hidden thing that you wouldn't be so easily measured would be, say, whether or not the subject was resting or traveling. So those are sort of two different categories of movement, but maybe you don't know quite how to define them. But you suspect there's some hidden process there that maybe is going on. Another example that is kind of like something we in the notes, but we didn't discuss at all, is like some sort of finance thing. So we'll say like variance of relative return. So that means like if you have some asset, we're talking about the variance of like the price of the asset today divided by the price of the asset yesterday. So something like that. So that's your process that you're measuring. And then the other thing, the unmeasured thing might be, let's say, there's different ways to phrase this idea here. You could say like economic climate, or let's do this. We'll say like investor sentiment. I use that word sentiment because I've seen this kind of thing done in some master's dissertations and probably lots of other places, where you like say look at Twitter, look at millions of tweets or something, and try to analyze from these tweets like what is the mood towards Apple stock today or at the time of interest here. And maybe you have several categories like it a lot, like it a little, ambivalent, dislike it a little, dislike it a lot, something like that. And so there's this range of sentiments, or maybe there's a more broad scale of spectrum, a broad range of sentiments, not just quantifiable quite like that. And so I want to point out a few things. So first of all, this guy is continuous in principle, as is this in principle. They probably have some limiting units or something. this guy's discrete. This is binary, this is binary, and this could be binary, or it could be a lot more complicated. So these are just some types of examples. Another one, there's lots of like biological examples you could consider, but I thought I would do this sort of, I find this example kind of fun. So imagine like, I don't know if you've ever had something, there's a medical device or procedure called an EEG. I forgot what that stands for. Electroencephalogram or something like that. It's some kind of basically a collection of like electrical sensors that they put on a person's head. So we'll say this is a probe voltage. So it's like some wires all over the head, and I think it just measures like potential differences between the two, many different places on the head, say. I'm not actually sure exactly what it measures, but some kind of continuous process. And then on the right, the hidden Markov process, we'll say this is like thinking. Up, down, left, or right. The idea here is that maybe there's a person's wearing this device and you're measuring all this electric activity in their brain, and you don't know what sense to make out of it necessarily, but maybe they've been told to try to like use a controller for a game or something like that, and so they might be, or maybe they're not even touching any controller because that's maybe a little easier to measure. Maybe they're just thinking up, down, left, or right, and so you have to somehow judge this from the probe voltage. I'm not sure this is the best example because maybe the thinking up, down, left, and right, or right, is something that's relatively measurable, because you could tell the person think left, think right, and so on. But anyways, these are just some examples to kind of get your creative thoughts going. There are a lot of different reasons that you might want to develop a hidden Markov model, and we aren't going to look at all of the different things that you can do with them. In fact, we're only going to really do a kind of a limited thing. We'll see a couple of different ways to make predictions for the probabilities that describe the observed process. But we'll get to that later. I thought it would be useful to see kind of a list of things people kind of try to do with these models. So these are sort of perspectives, or you might say aims or motivations or motives. So these are basically things that one might want to do with a hidden Markov model. And again, we're not going to do all these things, but I want you to kind of have a feeling for things that people actually do. So the first, you can kind of lump these things into, roughly speaking, 3 categories. You're either interested in learning something about the hidden process, or you're interested in learning something about the observed process, or you're somehow interested in some combo or mix of those. But so let's see kind of what are some examples of these things. So let's say you're interested in the hidden chain. So interested in the hidden chain or the hidden process. Right, so for this, and we call those the states or the parameter process or the hidden Markov chain, whatever, a bunch of different names. So I'll just write over here S sub t. You're somehow interested in this. This is your kind of chief motivator. So one thing you might want to do is use the observed process as some sort of an indicator of what these are. So use the observed process as an indicator. You might say, like an indirect and noisy one. Of the states, or like of the sequence, state sequence. All right, so that's one motive. You might actually consider sort of the purpose of the hidden Markov model to be essentially to decode that sequence. So you could consider purpose. It's to decode, or you might say like extract the state sequence. And there are schemes for doing this. Maybe the one you might, if you want to look into this and learn more about it, because again, we're not going to be doing it here, is there's an algorithm for doing this called the Viterbi algorithm. So you can look that up if it interests you. But so this is sort of the rough idea of things you might want to do if your sort of main interest or object of interest was the hidden process. Alternatively, of course, it could be the case that you're actually mainly interested in the observed process somehow. So interested in the observed process. X sub t. So, I mean, for example, the obvious instance is here, like, you might be interested in the hidden process if it's something that you didn't know any way to measure and you really wanted to measure it somehow, like mood or something like that. Alternatively, you could imagine like maybe what you really want to measure or kind of forecast. Maybe you think you have some you want to think of like making some forecast or something for the continuous or for the observed process itself. So like, for example, if you were looking at some kind of financial measure for the observed process, like what did we talk about? The variance of the return or something like that. So in this instance, you might think of the states as kind of just nuisance parameters. So that is, you might think the states are not very interesting. But they're just somehow required to get an accurate forecast. So for example, you might not really care if you're trying to make some forecast for volatility in a market, say, of some financial product. You might not really care what is the sentiment of the investors, but what you care about is what is the actual volatility that is predicted by that sentiment somehow, or how strongly are those coupled or something. And maybe you then can concoct some sort of scheme for predicting the sentiment or something like that. Yeah, so this is just an example of how you might be interested in the observed process. And then the third, of course, is that you might somehow be interested in both, or some combination. But I won't really dwell on that. It's probably worth saying this second example here, or second kind of description of interests, is probably what is most going to look like what we're going to be doing in here. We're not going to be decoding the hidden process, and so really what for us, it might not really be the case that the hidden process is unobserved. It might actually be observable, but we want to sort of use that to make a forecast for this other process that I'm calling the observed process. This is kind of why there's multiple names for a lot of these different things, because the scenario and your motive might kind of change up how you want to interpret these different things. But so before I carry on, so we're going to give like a formal definition of a hidden Markov model, and then we're going to make a proposition for how you can kind of make a useful calculation with one. But before I do that, I want to introduce some new notation. We'll just say notation. And it might be the case that it's pretty obvious to you how this new notation is supposed to work, but there's enough chance for confusion that I think we should kind of be explicit and say exactly what it is we're trying to do here. So essentially, we're going to introduce a notation, a shorthand notation. So we'll use shorthand. And by shorthand, what I mean is notation that sort of hides some of the important information. Notation to do basically two things. So one, to shorten things, and two, so because equations would otherwise have been kind of long, to enable both discrete and continuous. So that is to say discrete and continuous x sub t state-dependent processes. Okay, and so here's what the notation looks like. So essentially we're going to be seeing a lot this symbol here. So f, and then its arguments are going to be lowercase x sub t, and then like given lowercase s sub t. Now, we haven't used lowercase x and lowercase s in our descriptions yet of this hidden Markov model, but you can kind of guess what they might be. They're going to be the values that are taken on by the different random variables, capital X sub t and capital S sub t. But so this also has, so there's some hidden information here. But so what we're doing here is basically, so that's part of the story, but we're also making it so that this, if it's a discrete x, then this thing is the probability that capital X sub t is equal to little x sub t, given that capital S sub t is equal to little s sub t. Right, so that's exactly what this thing is if x is discrete. So it's a PMF, probability mass function. If it's not, if x is continuous, then this thing is a probability density function, and so we'll say it's a probability density function for the random variable x sub t, and then it has its argument little x sub t, given that big S sub t takes on, oh, can't erase that somehow, takes on the value of little s sub t. And so this is a probability density function. Right, so what's improved here on the left-hand side is that this f doesn't say whether or not we're talking about a probability density or a probability mass, and that's probably something that's familiar to you from other classes in statistics. This, however, this is a little more risky at times. It doesn't say what random variables we're actually talking about, and it doesn't say are these like equal to these things, or like in this case, or is it more like in this case? So anyway, so there's some information that's kind of buried in this notation, but hopefully it kind of makes things more effective. And I also just want to mention kind of an interesting thing. So So this notation, you can, so if, like, suppose that you have capital N states for these guys. Your state space has capital N elements of values that the hidden process, the hidden chain can actually take on. Then you could think of this thing. So then f of, and you can use this notation, s sub t given s sub t minus 1. Now notice, so like there's no x's here, so what this means is this is meant to be big S sub t is equal to little s sub t, and this is yeah, let's just write it out. So this is actually equal to the probability that big S sub t is equal to little s sub t, given that big S sub t minus 1 is equal to little s sub t minus 1. And you can see it gets long, right? So this notation is hopefully helpful. It hopefully gives us some, saves us having to write a million things over and over again. So hopefully it's valuable. But so that quantity right there, it should look familiar to you. This is a one-step transition probability matrix for the hidden Markov chain. But if you wanted to use it in the usual way, so notice, if you tried to use the ordinary notation, so it'd be like this thing here, f s sub t given s sub t minus 1. We've been calling that like little p with some subscripts, right? So now you'd end up with little p subscript s subscript t. And then the second index is subscript s subscript t minus 1. So it gets pretty clunky. The things get pretty awkward. You've got subscripts going on, and it gets to be a bit of a pain. So just be aware of that. This notation, sometimes it's cool. Hopefully you can see from this that this new notation over here, it saves us in a lot of ways. So it makes it a lot easier to express this transition probability matrix. Like, this is pretty awkward. This is long, but it's not as awkward. And it's certainly not as long as this thing here. So yeah, I don't know. It has its utility here. But yeah, so let's go ahead and make our formal definition of a hidden Markov model, right? So here we go. So this is a definition of a hidden Markov model. So we'll say a hidden Markov model, it's a pair of stochastic processes, or it's a doubly stochastic process. Right, and so we'll say it looks like this. Capital X sub t, and then capital S sub t. They come in pairs, such that t is 1, 2, 3, and so on. And these things, well, I don't know, I guess I don't know if I can fit this in. So x of t are the observations. The s sub t are called the states. But as you've seen already, we have different names for these things as well. So x sub t are the state-dependent observations. Yeah, and this thing, s sub t, This thing is an n-state Markov chain. The important thing here is Markov chain, not the n. All right, and that is to say it has the following property. So you can say that the probability that s sub t, so I'm using the longhand notation here, is equal to little s sub t given, and then you write out this whole history. S sub 1 is equal to little s sub 1, s sub 2 is equal to little s sub 2, and then so on all the way up to t minus 1. This conditional probability is the same thing as if you just knew the most recent time. So I'll write that like this. Sorry, given. Right, so that's just saying that this is a Markov chain, and in the shorthand notation, so we'll say also written in the shorthand notation. So we'll say this is f little st given little s1 dot 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 up to little st minus 1. This is just equal to f little st given little st minus 1. So you can see it really saves us a lot, this notation here, at least in this case. It's conditional on the current state. So how do we write this? So and conditional on the current state. It's quite a mouthful, this definition. The observations are independent of the states and the observations at other times. Oops, erase. At other times. So we'll put this long mouthful of a sentence into an equation which is more concrete. So what we're saying is little f of little x sub t given, and then let's say you had a whole bunch of information, that you had x1, x2, and then all the way up to xt minus 1. And S1, S2, all the way up to ST. This is actually just the same as f of xt given st. So it's sort of like the Markovian property, but it's a little bit different because we've got two different processes linked together here. And so what we're saying is this conditional statement, so this thing, conditional on, how do I say it? Conditional on the current state. It doesn't, this stuff does not, adding this to the conditional statement doesn't give you anything. So it's actually just equal to this. All right. And so there's another way you can kind of express this. So therefore, if you had a sequence of these, so you can write this. So f xt, or sorry, I don't want to say t, 1, x2, up to xt, given s1, all the way up to st. This thing is just equal to a product for n equals 1 to t of these simpler things. Oops. Come on, pen. Like that. So that's the definition. It's quite a lengthy definition, but I hope you see kind of what this doubly stochastic process is about. This hidden Markov model. All right, so there's a lot of things that you could want to do with hidden Markov models, like I've said, but we are going to focus. So here we're going to focus on one specific calculation, which is actually the building block, one of the fundamental building blocks for all these different things you can do. But it looks like it's just useful for kind of one of them. But so what we're going to do, so we will focus on computing one kind of thing. So we're going to look at how to calculate this kind of thing. So the probability density or mass function for a sequence of observed values, or a sequence of values for the state-dependent process. Like that. And so that's what we're going to be focusing on how do you compute this, and we're going to see a couple of different ways. It's going to illustrate a little bit how you can get kind of some improvements. So the first way we're going to see is what we'll call like the brute force method. So this one is a proposition that we're going to prove in the next lecture. And so this is called the brute force method. Well, I'm calling it that. And I just want to reiterate, so it looks like what we're doing is we're just trying to figure out, suppose you have some model for the hidden Markov process. How could you then use it to make forecasts or predictions for what you expect for the distributions of these state-dependent process values? But it actually is the case that you can use this for a lot of other purposes. But it sort of seems the most clear that that's what you would do with it. But you can use it to, say, fit models to data, or to do some sort of model selection process, or to actually do the decoding of the states that I described before. Okay, but so let's get to the proposition. So the proposition, how do you do this? The simple kind of, well, I don't know if it's simple, but the sort of straightforward kind of brute force method. And so the straightforward / brute force method looks like this. So we say f, this left-hand side, the thing we're interested in, right? So this quantity is equal to, and it's a bit of a long expression here, and we'll prove this again, but we'll do it in the next lecture. So this is a sequence of sums. So a sum from S1 equaling 1 up to capital N, and then there's a sequence of these things, and then it finishes with S sub capital T equaling 1 to capital N. Remember, capital N is the number of elements in the state space for the Markov chain, for the S process, right? And then we write f of S1, right? So I'm using this shorthand notation all over the place. And then we have a product for index, say A equals 1 up to capital T of these guys, f of x little a given s of little a. And then another product, I think I can fit this in here, for B equaling 2 up to capital T of f xb. Sorry, got this wrong. These are s's now. SB and then SB minus 1. So it might not be clear to you how this could come to be, but again, we're going to prove this in the next lecture. But so this is the so-called brute force method. And before we kind of talk about it. Well, before we won't do the proof today, but I want to now just sort of pause and think about what do we see here. So notice a couple of things here. So first of all, this is very expensive. Computationally expensive. So think about what's going on here. So this piece here, all these sums, right? These guys, each sum has capital N terms, and there are capital T of these. And so this is capital N to the T terms to add. All right, so that's already pretty big. And if you look at in detail at this piece, what do you see? So there's the multiplication here, but then look, there's a product of length T, and there's a product of length T. Each of those, so each argument that gets fed into this sets of sums has T squared multiplications. So how do I say this? So each term, or each argument, I don't know how you say this, has capital T squared multiplications. Yeah. Yeah. So it's a lot. And so let's think about what this, so what this means is this is a sort of cost is something like T squared times N to the T operations, which might not seem like a lot to you, but look at that. T is in the exponent here. And so here's just an example. So let's suppose you had what might seem like a modest case. Let's suppose you had n equals 10. That might seem kind of elaborate. So that means your hidden Markov chain has 10 different possible states, and most of the ones we were talking about in the sort of motivational stuff only had a couple. So this may be a little high, but maybe not. Maybe those were like my lame examples, and there's a lot better ones out there. And let's suppose you had 16 time steps, right? So what does that give you? So that gives you T squared N to the T is approximately 2 times 10 to the 18 operations. Now, what does that mean? So 10 to the 18 operations. So let's say your computer can do 1 billion operations per second. That's like a gigahertz, right? So that's 1 billion is 10 to the 9, right? So that means every second you can do 10 to the 9. So we need to then do 2 times, so what does this mean? Like, so if you're operating at a gigahertz, this means you have to do 2 times 10 to the, so what is it, 18 minus 9, 10 to the 9 seconds. Which you might not know kind of what that means. So 2 times 10 to the 9 seconds, you might not know, but a year has about 3 times 10 to the 7 seconds in it. And so this is about 100 years, something like that. So I don't know, maybe it takes 100 CPUs 1 year, or 1 CPU 100 years, or 1,000 CPUs a month, or something like that. But anyways, it's expensive, all right? Nevertheless, this is actually doable if these numbers aren't too extreme. If N and T small. It's certainly doable if they're super, super small. Like if we just give you 2 for each of them, say, then maybe you could work that out. You maybe even do it by hand. What would that be? That would be 2 squared times 2 squared. Yeah, I think you can do that. It is still actually significant. 16 operations, you know? So anyways, it's doable if n and t are small, but also it requires you to have a whole lot of ingredients. So if you have all the ingredients, or all the pieces that are needed, so let's think about what those necessary pieces are. So let's just take this. There's quite a lot of pieces, so let's see if we can kind of make sense of them all. So the first thing, so I think sort of break it down into several different parts. So the first thing is like this guy here, f of s1. So if you go back up there, you see him, see this guy right there, right? So then we'll have other pieces to talk about in a second. But so f of s1, this is, so this, you need this for s1 equaling 1 up to n, because there's n different values in the state space for the chain. And so in other words, you need the probability that S1 is equal to j for all j. And what is this? So you should think about this for a second. Just maybe make a pause and think. So this guy is the initial state distribution. Which we've been calling in previous lectures like U0. We started time at 0 in the past. So that's the state vector at the initial time, right? So that's one of the necessary pieces. So let's make a little divider here. The other necessary piece, so let's go back up here and see what's next. Next in line is this guy here. Let's just take it. Bring that down there and think about what this is. So this piece here, well, what do we need for this? Oh, and I should say, so how many of these guys are there? There's n different things you need to know for that. So this piece here, this is these are the same. So this is for homogeneous. Same. So this gets a bit easier. But what you need is, so for all a equaling 1 up to capital T, right? So those are the times. And you need this for all xa. And how many values will we say that there are of those? So this is the state dependent process. So I don't know how many values, it's not n. So let's say that there's like c values of those. It could be continuous, in which case it's a little bit messier somehow. But yeah, so and then you need this for all SA. And so how many of those are there? So those are the values of the state dependent process. So this is n different values. And so how many things are these? So you have t, how's this go? So you have t different a's, and then for each of those you need c times n. Or maybe they're all the same for homogeneous. So let's just say that it's homogeneous because that's what we're focusing on. And so for this, there's n times c different things that you need to have. And then the last piece, so what is the last piece? Let's go up there and look. The last piece is this guy here. So we'll take that and just sort of look at what it is. And again, we're going to prove why this brute force method actually works in the next lecture. But so what are these guys? Well, I hope just from our conversation a second ago, this should be kind of clear what this is. So this is for SB minus 1 equaling, let's say I equaling 1 up to n, and then SB. So this isn't the range of b's, this is the range of what values s can take. So this is, let's say, call this j. So that's also up 1 to n. And so those guys are, this is the equivalent of the Pij. These are the one-step transition probability matrix. And there's n squared of those guys that you need to have. But yeah, so these are the pieces that we'll deal with when we try to actually make these calculations in the next lectures. I hope everybody enjoyed that. We now have all the pieces in place to start to do the first kind of introductory level useful computation that you can do with hidden Markov models, that you could branch off from there to do a lot more things. And I hope you have now sort of an appreciation of kind of what the scale of the calculation is, so that when we look at the improved methods method in the next lecture, you'll kind of be able to appreciate that. All right, I'll see you then.